We'll get started in another few minutes here. Everything's been pushed back because of the 10-15 minute delay from the previous session. So.
Yeah. Hey. From? Oh, okay. Hey. Bristol. Okay. Yeah, this is Vijay. Hey, we met. Right. Hi, how are you? Good. How are you? Yeah. Glad to be, with you guys here. Yeah. Let's put it. Is it coming up? Should we connect this?
Can you take
It should be able to. Oh, it doesn't have that cable. Oh, it can only take a USB. Oh.
They have some other connectors in there too. Or somebody out in the audience may have one too. What size of connector?
Or we can get his laptop, no? Yeah.
What
That
size
can
of
connect.
connectors do you have though? If we could ask for some.
That should have at least this connector, yeah.
Okay, great.
Yeah. This is what connector is this?
It's the little mini HDMI thing that the Macs are using.
I don't know.
I don't think, no, it doesn't work there.
This will work? Oh, it does.
It does? Okay, let's give it a shot. That sounds
Let's
good.
try, yeah.
Wonderful.
I think it can connect.
Sorry. Maybe new glasses. Okay, good to go. here, but he's not back yet. So the video guys are here, but not the main AV techs. Do you want to try the other laptop though? If that might be another, because the Mac connector is probably wired for what the
No, I
Mac
thought it was
connector-
working, right?
It was? Yeah.
Oh, is it? Thought it displayed there. Oh, okay. Oh, okay. Yeah, I think you should do that. Just get this off.
We will not be needing this one. It's on the other side. Yeah, we should be able to use that. All right, let's see this. Okay, all right. Let's just take it out for now. Come back to it. Okay, all right, that works.
Mea culpa. Sorry. We're software people here, right? Got to work with this hardware. It's a great honor to be able to introduce one of my friends here, Vijay Agneeswaran from Impetus. We've worked together on some open source projects in the past, and Vijay and Vishnu are here to speak about distributed reinforcement learning with Spark. So without further ado.
Thanks, Paco. So we've been doing some work on building some machine learning algorithms over Spark. So as part of that effort, we are now on to this reinforcement learning. Vishnu comes from an optimization background. So we are now looking at trying to see if we can implement a distributed reinforcement learning algorithm for the energy market over Spark. So just to quickly introduce Vishnu, so he's a senior data scientist. He has a PhD from USF and has been a faculty in UWM for a while before he joined us. And I myself have been around for some time in this space and been talking in some of the Strata and the Spark Summits before. So over to Vishnu, and he can take us through some of the initial stuff on the reinforcement learning itself before I come back and talk about how we are actually implementing it on top of Spark. This is work in progress, so we have just in the process of finishing up the code. So we've not done large-scale testing and some of that stuff. So with that caveat, we'll go ahead. Yeah. Over to you.
All right, thanks, Vijay. So this is, like Vijay said, this is really work in progress, but the reinforcement learning stuff has been, I have implemented that before, but not on Spark, just regular C and whatnot. So the agenda for today, so I think this talk will be a little bit different than what you might have seen before. So I'll talk about what an electricity market is, and then why it needs to be modeled. In the first place, I come from a sort of a OR optimization background, so I'll talk about modeling a little bit more, and why it needs to be modeled. Then are there other markets that could need or use such modeling? And then talk about why reinforcement learning in particular. Obviously, different researchers have taken a look at electricity markets in different ways, and the way I chose was reinforcement learning for different reasons. Talk a little bit about background and basics, and then we'll get into the Spark discussion with Vijay, and he'll discuss any other options that are available for solving this model that we developed, and then briefly discuss some code sketches on Spark, and then we'll talk about ongoing and future work. So let me quickly take you to a picture of the US here. These are the electricity markets in North America. All the colors other than the green that you see are where there is competition in the markets, which means competing power generators have to supply what are called bids each day into the market, and then those get cleared using a complex optimization routine, and prices get decided. In fact, this actually happens every day of the market. So as you can see here, close to 2/3 of the US operates under this regime. So California has the CAISO, we have PJM, which is the Pennsylvania, Jersey, Maryland. We have the Midwest ISO, the Southwest Power Pool, the Reliability Council of Texas, and so on. So there's a lot of independent system operator-based markets where electricity is traded competitively in the wholesale side. So the idea was, prior to what we call as restructuring, if you guys recall, before the 90s, electricity was sort of a vertically integrated industry. Essentially, generation, transmission, distribution was owned by a single entity, and prices were set, and they were not set competitively. So in the early 90s or mid 90s, the United States government started to what we call deregulate or restructure these markets and introduce some competition in the generation side. There is some competition in the retail side in several markets now, but predominantly the generation side, essentially big generators were sort of forced to divest and break them up into smaller independent power generators. And now anybody with the right set of tools could really be part of the power market. So that's sort of the vertically integrated older structure. And we'll focus on the electricity market as it is today. So in this market, we have this handsome-looking gentleman here who's the independent system operator. So he's sort of the referee in this market. And what the referee does is essentially match supply and demand. And so we have multiple power generators, could be any type of generators. You have different types of load-serving entities, or your distribution side, who takes power and gives it to the consumers. And what happens is these competing suppliers submit what are called price quantity bids. Essentially, a bid is nothing but just saying, to supply 50 megawatts, I'm going to charge you $100 or whatever, right? Just a price quantity curve. And similarly, on the demand side, the load-serving entities submit what are called demand bids, essentially saying, I can consume so much of power for so many dollars. So the independent system operator is a non-profit entity, and they essentially match the supply and demand. Obviously, it's not a simple matching. It's a power network, so there's a lot of transmission constraints. There are power network-related constraints, voltage, current constraints, and so on. So I don't want to get into all the mess, but just think of it as just matching supply and demand and figuring out the electricity price. And the idea of why it needs to be modeled is that this repeats each day. In fact, it happens multiple times each day. So any power generator will submit 24 bids for all the 24 hours of the next day. And this market is cleared every hour of the day, right? So it's something that happens repeatedly. So I'm bidding, I'm making a decision today for tomorrow, tomorrow for day after, and so on, and this continues. So why does it need to be modeled? Like I said, to understand the long-term behavior of the market. And if you recall, the California energy crisis, happened because of a bad market design. So that wasn't foreseen by the market designers. And, the generators were able to jack up the prices, the distributors could not buy the power, and the market crashed. So to avoid those things, these things need to be modeled, and that was sort of the motivation when we began this work, 8 or 9 years ago. And then, studying the equilibrium behavior. What do you need to do, on a stable, market? What needs to happen? And assessing market power. Market power is essentially the ability of a power generator to raise prices and keep them consistently higher than competitive levels. That's market power. So you don't want people to have market power. If you recall, when there's a merger, there's always Department of Justice always intervenes, right? And the reason for that is to make sure that no player or no entity has too much market power and tweak prices as they wish. So that's the reason whenever there's a merger, the Department of Justice gets involved. So and then obviously investigating policy prescriptions is a big use of such modeling exercises, where you can, let's say, you can impose a carbon policy or a cap and trade policy and check how the market may evolve over a period of time. So that's a possibility. So this is the reason why these markets need to be modeled. So let's talk about the modeling approach itself. So like I said before, just to jog your memory, we said every day of the year or every day, I make a decision for tomorrow. For tomorrow, I make a decision for day after. So this sort of evolution has been shown to be a Markov chain. Those of you in computer science luminaries in the audience must know Markov chains and Markov decision process very well. So this has been shown to be, to be able to be modeled as a Markov decision process. The way we are doing it is, since there are multiple competing generators, we are modeling it as a competitive Markov decision process or a stochastic game. So essentially, multiple generators are making decisions, and the system evolves to another state, and they make decisions there, and so on. And by studying the system over a long-run horizon, I'm able to understand the evolution of electricity prices and any other parameters that you want to study, right? So, but the only issue with the competitive Markov decision process is that the solution, solving it is really difficult because you need what are called transition probabilities. Right, you need those probability matrices. That becomes difficult. So we kind of have a work around that, and that mechanism is called reinforcement learning. Reinforcement learning is nothing but neurodynamic programming, simulation-based dynamic programming, approximate dynamic programming. Different research groups call it using different names, but it is essentially a way to solve stage-by-stage decision-making problems using simulation. So it really falls under the paradigm of what we call as unsupervised machine learning. So we really don't have past data to work with. So we actually develop the data as we go along. So this is sort of, you model the system, and then you try different things on the system, and you learn as we go along. So we are going to simulate the system and learn things. So it's called unsupervised learning. It's called a model building type of learning. So just quick, a little bit of math here. We'll call B as the set of supply buses, M as loads, and N as generators. And X is defined as a system state. So essentially, if you think about Markov chains, you always need a state of the system. The state will force you to make a decision. The way you perceive the state is what will require you to make a decision. So every generator or every power generator sees the system in a specific way, and they behave accordingly. So that is what we call a state. And here we represent it using a tuple QTPT, and Q is the loads or the demands in the whole system, and PT is the price vector, and DT is the power generator's bid for the following day. X is the system state process, and D is the decision process. So together it's called a competitive. So these two stochastic processes together, it's called a competitive Markov decision process. And we solve this problem using an average reward criterion. I can talk about details offline if you guys are interested. And we call this reinforcement learning. So what I'll do is just give you a few basics of reinforcement learning. So essentially, RL is founded on two important principles. One is the Bellman's optimality equation, and the other one is the theory of stochastic approximation. Bellman's equation is really a mechanism to solve Markov decision process, right? And stochastic approximation is a way to find the expected value of a random variable using simulation. So when these two things come together, you're able to simulate the system and essentially learn what you need to learn about the system without having to know the transition probabilities. So that's sort of the idea. We're really trying to obviate the need for using transition probability matrices. And any reinforcement learning model typically contains 4 elements. The first thing is the system environment. In our case, it's the electricity system with the independent system operator sitting in the middle. Then you have the learning agents. In this case, they are the power generators who are trying to learn different things. And the set of actions for each agent. So essentially, every generator, I could have different generators, mind you, right? I could be a coal generator, there could be another nuclear power generator, and their cost characteristics are very different. And the way they act in the market is very different. So you have to keep those in mind. Those generators have to sort of, balance those, curves accordingly, the price offers. And then we have a system response. So the way you learn in a reinforcement learning model is by making a decision, and those decisions go to the system operator, and the system operator decides what the price is. So using that price, I can compute my reward. So I will know how I have done in the previous day. And that will help me to make, hopefully a better decision going forward. So you're trying to reinforce good behavior and penalize bad behavior, right? Just like any other learning mechanism. So just a quick digression here, other applications for such models there are, and I've worked on some of these. So carbon allowance markets can be modeled as these, carbon credits, and then capacity expansion planning problems also. Anywhere you have stage-by-stage decision making, it is possible that you can use reinforcement learning. So let me go to this specific case of how it works in the electricity market. So we have the independent system operator, and we have different system states as perceived by different generators or different agents. So I have, let's say, n agents in this model, and now agent 1 takes an action, agent 2 takes an action, agent 3 takes an action. And what they do is, along with taking actions, they have the ability to explore and exploit, and many learning algorithms have this ability, right? So this way I can take my best action if needed. That's called exploitation, where I exploit my best greedy action. And I can explore my action space by using a learning parameter, and I can explore the decision space to make sure I try different actions. And based on these actions that are received at the independent system operator level, even though I'm showing these sequentially, these happen really in parallel. So that's where the whole, Vijay is going to take over and talk about the implementation of this in a distributed setting. So the idea is that the actions go to this independent system operator, and the system operator essentially solves he uses a market clearing mechanism and clears the market. So he has to make sure that the supply and demand meet each other and match based on transmission constraints. And then they get a price, quantity, and reward back, all of them, all the agents who are participating. And that will result in a system state update, which means the system moves potentially to a new state, right? Or it could come back to the same state. So that's what happens. So every time decisions are taken, the system gets updated, and decisions are, and this is used. So this, learning of the price, quantity, and reward are used by the power generators to update their knowledge base. So knowledge base is nothing but a lookup table. So essentially, it tells you in what state, what actions you have, and what is your, the value that you have in every state action combination, right? So that's sort of your lookup table that tells you how do you behave when you reach a specific state in the model. And all the generators or agents update their knowledge base. And then this continues until a predefined set of convergence criteria. I didn't go into the details here, but there's some other stuff here, but I'm not including that. So with that, just want to point out that, like I said, the action are taken in parallel, and the updating happens in parallel. Just the calculation with the independent system operator is something where information is gathered, some calculations are done, and stuff is sent back. So with that stage, I'll hand it to Vijay here.
Thanks. So before we go on to actually how it is implemented, I would like to take a couple of minutes and talk about why we chose Spark and what's the real funda, right? So as we can see, right, this is a typical iterative kind of computation. So we all know that Hadoop MapReduce is not well suited there. There are going to be a lot of overheads involved. So of course there are choices which have kind of worked around the Hadoop MapReduce, Twister, and Hadoop, and Apache Hama have been there. So however, the main question there is in terms of fault tolerance, none of them provide the fault tolerance that Hadoop provides, and their enterprise readiness is also kind of under question. So for these reasons, we didn't plumb for any of these, and of course GraphLab would have also been a good choice because as we can see in the subsequent slides, this could be modeled in terms of a graph. So GraphLab might have been a good choice, but then again the caveat there was though they did have a distributed snapshot implementation, but then there was no automated way to recover from the those snapshots, and one would have to manually start recovering. So that was one of the challenges we faced. Obviously, right, so all these kind of lead us to saying that Spark would be the ideal choice, and because it provides the fault tolerance that Hadoop can provide. At the same time, the performance-wise, we would be in much better shape. The other thing, that kind of prompted us to use Spark was the fact that, we could start, the way Vishnu had described the problem is, this is more of the day bidding kind of scenario, but we could also transition to the spot bidding, which would mean that, we would then start dealing with real-time data and start doing things in real time. In which case, if we had done it on any of the other frameworks, doing it in real time becomes much harder. Whereas with Spark, the transition would be very smooth. We could do it in real time as well. The day we want to, we can switch to real time thing as well if we use Spark streaming. So really the way we have kind of thought of implementing this is as follows, where each of the players become vertices of a graph. And of course, it's not a very complicated graph in the sense that it's a simple graph with these vertices pointing to the master. And so the master kind of runs the clearing algorithm, right? The market clearing algorithm, as Vishnu had articulated it. So that's what the master does. And basically, all the players, they have essentially the knowledge base, and they try and build the knowledge base. So what we're talking about is mostly the training phase, where the knowledge base would have to be built by the respective players. And so this happens essentially, one can see that, it happens in lockstep, because first the players submit the bids, right, to the master. And master, once he receives the bid from all the players, runs the clearing algorithm, and then gives out the respective rewards to each of the players. So this is, in a very simple setting, this is the classical case of the BSP, the bulk synchronous parallel. So the way we have implemented in Spark is to use the BSP construct. So we've used graphics, and so these players become vertex programs, in the in graphics. And then there is, of course, a merge program, which acts like the master, right? And so that is essentially, running the market clearing algorithm. So this is in essence, right, the way we are kind of implementing it. So each of these, the single BSP step, of course, the first step is slightly different because it kind of starts initializing the knowledge base. But subsequently, the way it works is each of the master sends back a reward, to each of the players. And the players then perform the computation of the next phase and update the knowledge base, and then figure out what should be the next state, right? They compute that, and then send the reward to the action to the master, who again performs the clearance, right, based on the bids received from all of the players. And that is in essence the single BSP step. So the master would act as a barrier and make sure all the bids are received before going on to the next step. So this is in essence how we have implemented. For some more details, we can quickly get on to that. So the reward matrix is essentially the knowledge base that gets calculated, right? And then we are modeling this players as RDDs, and with, of course, the get action and update R matrix as functions. Yeah, essentially this is how the code looks like. Very crude, so that's the reason we, haven't still put it out in the open source, and it still needs a lot of work, but so we're getting started, the essentially using the filter constructs and trying to realize this matrix and the way the metrics are to be updated. So this is how it is. We can go over the details if any of you are really keen on that. So the other part is, of course, the master, right, which would run the market clearing algorithm. So this is essentially a pre-gel construct that we are using here, in graphics. So pretty much the merge message, would act as the market clearing algorithm essentially. So that's the essence of the implementation. It's work in progress. So pretty soon we will have some results out. As we are talking, the implementation is being finished up, and they're trying to get it to run and make sure it's working correctly. And we will have some results out pretty shortly. So would be happy to take questions before just one slide where would like to explain what's the way going forward. So the way we are looking forward is to make sure something like giraffe-like APIs can be there for graphics as well. where it would be pretty simpler and more direct to kind of specify the master and slave codes, whereas currently it seems little implicit, right, rather than being explicit about the APIs. And again, the barrier could also be specified in a very explicit way. That's something we can look at. And of course, the more complications, right, can be brought in, and we could start applying this to the other scenarios that Vishnu had kind of outlined. And of course, we would also like to compare with, for example, GraphLab or Stratosphere, how they perform, right? Since we can achieve similar BSP implementations there as well. So that's something we look forward to doing. So we can take questions if people have any. Yeah.
When there's an action request, is there a cost associated to that action? And when there's a reward, can the reward be negative? Represent like a punishment?
Reward, so ideally the power generator, so what you do is if you have a marginal cost function, typically you would not bid below your marginal cost.
Not here, yeah.
Okay. Sorry. So the question was, can there be negative rewards, sort of like a punishment? So the answer to that would be no. And the reason is you wouldn't bid below your marginal cost. Usually you sort of either bid at cost or a little bit above. So you typically cannot have a negative cost. You might have low profit. That is good enough reason for you to not take that action again or take it a little bit less often, I suppose.
I was asking if there's a cost associated to performing the action.
No, there is not, no.
You cannot flood or...
No. Well, you're required to submit. You're required to submit an action each time. So there is no cost for submitting or taking the action. Yeah.
If I understood correctly, you just showed like a framework to simulate evolution of the system, but can you learn from the data what's the actual dynamics, the utility functions, the transition matrices?
Right. So that is what we are looking to avoid. Having to learn the transition probability matrices, that becomes a lot more complex. So what we're trying to do is have power generators take or try different actions, and when those actions go to the central entity, the entity essentially decides what the quantity of supply the following day would be, and those could be used to calculate your prices. So essentially what you're trying to do is, this is a discrete stochastic model, so you sort of predefine what your states of the system are and what the actions for every generator. And you're trying to essentially, it's really sort of a trial and error based learning that you're trying to do. I don't know if that fully answered your question. We can talk offline if that. Okay, well, you decide, you're the boss here.
Just
So
curious to follow up on that.
Okay,
Have you looked
sure.
at using symbolic regression or genetic programming in terms of being able to evolve some kind of a smooth gradient on that?
No, I have not. That's something to look into. We haven't tried that yet. Yeah.
When you train the model, or when you simulate this on historic data, how can you calculate the model efficiency? Because you know what happened in the past, but you don't know what would have happened if you take a different action according to whatever policy your model calculates. So how do you practically go about evaluating the model
Right.
performance compared to existing state?
Right. So currently, the way this is a model building mechanism, so we don't have any historical data. So I'm actually learning on the go. As I'm learning to take better decisions, hopefully my profit will increase. As I take better and better decisions. And obviously, at a point, you will know. The idea is that at the end of the simulation run, I would know what decision I need to take in every state. So which means, the way I've classified the state is a set of demands and prices. So if I have a sort of a projection or a forecast of, if it's summer's time, if my demand would be in this region, I might, with some probability know what action, I need to take in this particular state. So that is how you would proceed. Obviously, there's, I guess you'll have to, take the electricity price on that particular day to validate your model to be able to see if, the players behaved as they're supposed to have behaved. Yeah. Yes, please. Okay, I'll go with you since I saw you first.
So I have a question about it seems like the way you describe the reinforcement learning is not fully distributed because you have a central bottleneck
Sure. That's a valid question. Some of the reasons I kind of outlined, why Spark. So of course, MPI is the extreme kind of choice, the classical choice. But of course, I could have gone with the Hadoop or any of the others. And I kind of said one of the reasons was, of course, in terms of if the number of states becomes very high and number of players are also very high, right? Then the number of states could become exponential, and you will have problems in modeling that, which is why you need to have a distributed realization of it. And of course, in a distributed realization, there could be various choices. And I think Spark is a good fit because the BSP, for example, the graphics kind of realizes the BSP in a very natural way. So I think it's still a good fit. That's my opinion, yeah. Some of the challenges. The main thing was to be able to model it, appropriately. What's the right way of doing it? So initially, we weren't sure, right? For example, should we use a BSP or not? So those were the challenges. Now we are in a stage where we are looking at the implementation is good. We've done that, but we need to look at the results and how accurately have we implemented the algorithm and things like that. Those need to be explored. Those would be the real challenges. Other than that, we did have some challenges in terms of the APIs of exposed by graphics itself. That's what I was saying, right? I would ideally prefer Giraffe kind of APIs, and which are pretty easier to use, but where, for example, the master is pretty implicit and the merge program is actually running the master. So we had to kind of figure out some of these things. But yeah, these were the issues. Yeah. Sure. Yeah, you had a question, right? Go ahead. Oh, okay.
Have you thought about making your update steps randomized instead of batch? So right now you require all of the parties to respond before you can actually update.
Right. Does it make sense to have randomized?
So you're saying make updates to your knowledge base at random?
Not at random. So there are randomized algorithms which are extensions of batch algorithms.
Okay.
For example, you can have a randomized k-means for k-means where you don't know exactly how many parties are there, but the expectation is known. So for example, if you have 55, on average you have 55, more or less.
Okay. Yeah, that is something for reinforcement learning I'll need to look into. I don't know if that's available or not.
Make it more robust, it will be a small change on your.
Right. Yeah, that's something we could think about.
We could explore that. Yeah. I think he had a question.
Yes, please.
Yeah, just to build off of this question a little bit more. Being that you don't have historical data sets to train off of, can you explain a little bit more about how you can validate your model? So where is it in your forward learning process that you ensure that those decisions and their outcomes, how do you ensure that those are actually represent what is reality?
Right. So the question is again validating the models. Obviously, for unsupervised learning, validation is always one of the biggest challenges. So in some of the papers that I've written, we could take like a test scenario that was pre-published, and we were able to get similar results using our learning algorithm, the profits and whatnot. So that is probably a way to look at it. For obviously for large-scale systems that you haven't modeled before, validation is always up in the air. I mean, that's a difficult thing to do. Yeah. But one of the things that you could also do is make your system the action choices essentially make them quite really discretize them very, very finely to be able to try all possible combinations. But obviously that has an expense on computational time, so you have to sort of make that trade-off a little bit carefully. That could be a way to try all different possibilities. Yes, please. Sorry, you have a question.
So since you've got kind of like agents bidding against each other, I mean, is it expected that the system will evolve towards some kind of better equilibrium state? I mean, is that kind of
Yes. So that's the goal really. So of the study, our goal is that hopefully learn a stable equilibrium. I don't want to call it Nash equilibrium. I'll get into all kinds of trouble for saying that. But some kind of a stable state where all generators have learned what they need to do in every state. So Nash would get me into trouble, but we call it an equilibrium, a sort of a stable state. Any other questions? Okay. All right, thank you.
Laptop is what worked.